Welcome in our day's class. Today we are going to look at chi-square test of independence. This is one of the non-parametric tests used in research. And I want us now to look on how we can get this statistic and how do we use it. But before we get there, I'll start by defining a few terms here and there. Then we'll be able to move on in our class so that when we use these terms, we will not be using them with a lot of difficulties. I will start by defining what the chi-square is. Chi-square is used to determine whether there is or there is no, there isn't any significant association between two categorical variables. The chi-square statistic, as I said, is an unparametric distribution-free tool designed to analyze group differences when the dependent variable is measured at a nominal level. Now, the two variables that we are dealing with may be dichotomized, meaning two, or they might be many, and here I'm using the word polychotomized. Unlike many other non-parametric and some parametric statistics, the calculation needed to compute the chi-square provide considerable information about how each of the groups performed in the study under consideration. And the richness of the details in chi-square allows the researcher to understand the results and thus derive more detailed information from this statistic than from many others. The chi-square is a significant statistic. And in order for us to know the strength of the statistic, because it only gives us the association, if we want to know the strength of the statistic, we have to follow this with Grammar's 5 test so that we may know the strength of the test and be able to know how this association is, because we are going to get the test itself from the either SPSS, but we must follow, if we want to know the kind of the strength, if there is an association, we want to know if this association is strong or weak, we must follow the test with Grammar's 5 test so that we know the kind of the association we are talking about or the strength of the association we are talking about. There are advantages of using the chi-square, and they include: one, its robustness with respect to distribution of the data. Second, it is to compute. When you are doing it manually, you can compute it, and you can compute it fairly faster. And its flexibility in handling data from both group and multiple groups. The data is more flexible. And as such, for these three reasons, it's good when we are using the chi-square statistic. There are several terms I want us to deal with in this study. Before we study doing the computation, there are several terms I would like us to deal with or to define, because we'll use them in our class today. And it's important that we understand these terms and their meaning earlier now, so that when we'll be introducing them later, we are at ease when they are introduced. The first term we are introducing here is null hypothesis. Null hypothesis. And this hypothesis states that there is no association that exists between two variables in the population. And thus, therefore, the variables are statistically independent. I will illustrate it by an example. If you're having two teaching methods, let me say you are having an online method and a face-to-face method, and you want to see which method is superior. So we say that method A and method B, you are comparing their superiority. Now, this null hypothesis assumes that the two methods are equally good, that there is none that is superior. There is no association between the two methods. The two methods are equally good. And this is a null hypothesis. Then I have another hypothesis, which is not null. We call it alternative hypothesis. This hypothesis proposes the two variables in a population are related in a way. Thus, if we are considering the example used above, that method A is superior to method B, then this is no longer an null hypothesis, but is an alternative hypothesis. If you put one of the variable above the other, then we say that this is an alternative hypothesis. Remember, we have said in a null hypothesis, we stated that there is no association that exists between the two variables under consideration. Another term we are looking at, or we want to define before we get into computation of the chi-square, is degree of freedom. Now, degree of freedom denotes the extent of independence or the freedom enjoyed by a given set of observed frequencies. In this case, if we have n observed frequencies, which are subjected to k independent constraints or restriction, then we have number of frequencies, which is n, minus the number of independent constraints, which is k, giving us the degree of freedom. In our case, we are going to have columns and rows. And when we have columns, rows and columns, it can be easy for us to calculate the degree of freedom. And this one can be given by, you take the number of rows minus 1, multiply by the number of columns minus 1, you get the number of the degree of freedom in the data you'll be dealing with. Then I have a contingency table. This is a table prepared by enumeration of quantitative data by entering the actual frequencies in every cell we have. So we are going to draw a table, and on one side we have the variables we are considering, and also at the top we have also the variables we are considering, and in each cell we enter the actual frequencies. And when we enter the actual frequencies in this table allows us to calculate the chi-square statistics. Now, this contingency table comes from the Latin word con and tencere. Con and tencere. Now, con means together and tangere means to touch. So when you put together, this is also called an association table. We will see how we use this table in our calculation as we move in this class. Also, another term I want us to, another term I want us to use in this class is the parametric and non-parametric. But let me wait. I will introduce them later in our classes. But how can we apply chi-square tests? We apply chi-square tests to test in 3 ways. One, we apply chi-square test in the test of goodness of fit of the distributions. Second way where we apply the chi-square test is the test of independence of these attributes. And the third way is the test of homogeneity. Let me look at the goodness of fit of distribution. What is it? This is the test that enables us to see how well does the assumed theoretical distribution, such as the binomial distribution or the Poisson distribution, which we call normal distribution, fit to the observed data. In this case, the chi-square test, the symbol for a chi-square test is x squared. So x squared, there is a formula we use for the chi-square. So in this case, the chi-square test, which is x squared, equals to numerator, or representing observed frequencies, and E representing expected frequencies. Both of them are squared all over the expected frequencies. So the formula is x squared equals to bracket or minus E plus the prefix square, and then on the denominator we have E. O is the observed frequencies and E represents the expected frequencies. We'll see how we use this formula later. Now, very important for us to put in our mind, if the chi-square calculated is greater than chi-square depulated with a number of given degree of freedom, then we reject the null hypothesis. I'll repeat. If the chi-square calculated is greater than the tabulated chi-square with a given number of degree of freedom, then we reject the null hypothesis. But if the chi-square calculated is less than tabulated chi-square with a given number of degree of freedom, then we accept the null hypothesis. Let us see how we use the chi-square in the test of independence. Now, the test of independence enables us to explain whether or not the two attributes are associated. So we are looking at two variables. If we are looking at the association of the two attributes, whether they are rated or not, then the test, the chi-square test we carry is the test of independency of attributes. Now, also very important to note is when you calculate the chi-square and you find that the calculated chi-square is greater than the tabulated chi-square at a given level of significance for a given degree of freedom, then the null hypothesis is rejected. And we say the two variables are dependent. When we reject the null hypothesis, it means that the two variables are dependent. And if the chi-square calculated is less than the tabulated chi-square, or we call them the critical values from the table, then the null hypothesis is accepted, and then we say that the two variables are independent. We will see how to apply these principles later in our calculation. When the null hypothesis is rejected, it can be concluded that there is a significant association between two attributes. Let me repeat that very important point. When the null hypothesis is rejected, then a researcher can conclude that there is a significant association between the two attributes. Now, I pause there and ask a question. What do we say when the null hypothesis is accepted? What will be the conclusion when the null hypothesis is accepted? Let us move on. The test of homogeneity. The test of homogeneity. This is the test that is used to test whether the two occurrences follow a uniform criteria or not. So when you are testing two occurrences and we want to see whether they are uniform or not, we do a chi-square test, and this test is called the test of homogeneity. Now, if the chi-square calculated is less than chi-square tabulated, then the null hypothesis is accepted, and it can be concluded that there is uniformity in the occurrence of events. In our class today, I want us to consider, or we are going to look at, we are going to calculate the chi-square of independence. But before we get there, I want us to look at the assumptions that we must be able to fulfill in order for us to do the calculation of chi-square of independence. Now, the first assumption that you must have is that the two variables you are looking at, or you want to look at the association, the two variables should be categorical. They should be categorical. Second, the number of respondents, if you want to use chi-square test, the number of respondents or tallies in this matter in either cell must be 5 and above. The number of respondents, in other words, the tallies you want to calculate, I want to put in each cell, it must be above 5. Number 3, the independent and dependent variable must be mutually exclusive. The independent and dependent variable must be mutually exclusive. Number 4, this data must be arranged in a contingency table. Number 6, the respondent must be randomly sampled. These are the assumptions, and we are on assumption number 6. Let me repeat these assumptions. There are 6. The first one, the two variables should be categorical. In other words, should be measured at nominal level. The number of respondents we are calling them tallies, in either cell must be above 5. The independent and dependent variables must be mutually exclusive. Data must be arranged in a contingent table, and the respondent must be randomly sampled. So there is also the limitation for these chi-square tests. Now, if there are so many categories, it might be difficult to interpret this data. And as such, the Cramer's 5 produced may be very low, and as such, it's difficult now to tell or to show the kind of association that exists, or the strength of the association that exists between these variables. Another thing you should put in mind, that a participant must be independent, meaning that an individual can not fit in more than one category. They talked of mutually exclusive. If a participant can fit into 2 categories, a chi-square analysis is not appropriate. Now, we have talked about random sampling as an assumption. And because of this, chi-square test does not give much information about the strength of the relationship. And I said, in order for us to get the strength, we must follow with another test. Procedure of calculating a chi-square test or chi-square statistic. You must, there's procedure number 1. You will propose an null hypothesis to state whether the 2 variables are independent to each other. So the first thing, you have to propose an null hypothesis and state that the 2 variables are independent of each other. So the null hypothesis you are proposing is that the 2 variables are independent. There is no association between variable A and variable B, which you are studying. Or else you have an alternative hypothesis. But usually we test the null hypothesis. Procedure number 2, you have to draw a random sample and classify the subject into 2 or more variables. So you have 2 or more variables, and you have to draw them randomly. And 3, set up a contingency table with the variable indicated in the row and another variable indicated on the columns. So you have one variable going to the columns and another variable coming to the rows. Now, when you do that, after drawing your contingency table, now record the observed frequencies in the proper cell. Record the observed frequencies, and after you've done that, there's something we call marginal totals. These marginal totals, I'll show you how we calculate them later. Now, from these marginal totals, we derive the expected frequencies from the observed data. We derive the expected frequencies from the observed data. We are on procedure number 5. Then we go to procedure number 6. We calculate the chi-square and compare the calculated value with the critical value that we get from the tables. From in the table, we also look at the level of significance, and also we consider the degree of freedom. Then number 7, if the calculated chi-square value equals or exceeds the value in the table, that means if the calculated chi-square is greater than the value that we find in the table, we call it critical values, then the finding is significant. The finding is significant. Very important in statistics. And when the finding is significant, then the null hypothesis of independence is rejected. You then conclude that the two variables are dependent or related at a given level of significance. If the calculated chi-square is greater than or equal to the value in the table, and these values, you call them the critical values, then the finding is significant. And the null hypothesis of independence is rejected. Very important word, rejected. Then you conclude that the two variables are dependent or they are related at a given level of significance. Also, very important, if the calculated chi-square value is less than or smaller than the value in the table, then the null hypothesis of independence is accepted. This means that the finding is not significant. And the conclusion is that there is no sufficient evidence of relationship between the two variables. Now, let us get to an example, because I've given a lot of theoretical explanation, but I want us now to get to an example. There are 500 voters, and a researcher wants to know whether there is an association between the gender and a political party of preference. So a researcher goes out and he wants to study whether there is an association between gender and the political party of preference. And this researcher surveys 500 voters. So when you look at the variable gender, you can get two variables from it. You can get female and male. And when you look at political party as a variable, you can have several political parties. So this is a categorical variable, and this also might be a categorical variable if you are in a political environment where there are only two parties. But when you are in a political environment where there are several parties, you can enumerate them. Now, we want now to look at how we can go on step by step in calculating the chi-square and see whether there is an association between the political party and the gender here. So in this survey, the parties we are going to use are Jubilee, because of course we know in Kenya we have these parties: Jubilee, CORD, and Independent. So there was one candidate who was Jubilee candidate, CORD candidate, and Independent. So we are going to draw a contingency table. Before we go to the contingency table, we thrust by the first procedure. Let us state the null hypothesis. And the null hypothesis we are stating here, that there is no significant relationship between gender and the voting preference for the political party. There is no significant relationship between gender and voting preference. And we are going to look at this at the 0.05 level of significance, because there are several other levels we can look at, but we are going to look at this at a level of 0.05. That is at a significance level of 0.05. Then these results are going to be reported in an APA format. Now we start. We move on to draw the contingency table. Come back to this one later, but let us draw the contingency table. This is the contingency table was talking about. That there is, on this side, we have the variable gender, and from the variable gender, we can categorize as male and female. And on the voting preference, we have the political parties. Here we have Jubilee, we have GOG, and we have Independent. So these are now the observed. These are what we are calling the cell. We have cell 1, cell 2, cell 3, cell 4, cell 5, and cell 6. This is where we are going to record our tallies. We record our tally in cell 1, cell 2, cell 3, cell 4, cell 5, and cell 6. The number of male who voted for Jubilee, we record them in cell 1. The number of male who voted for CORD, we record them in cell 2. The number of male who voted for an independent candidate, we record in cell 3. And the number of female who voted for Jubilee, we record them in cell number 4. The number of female who voted for CORD, we record them in 5. And the number of female who voted for the independent candidate, we record them in cell number 6. See how we record them. In this, we get that the number of male who voted for Jubilee were 200. The number of male who voted for CORD were 150. The number of male who voted for independent candidate were 50. The number of female who voted for Jubilee were 250. The number of female who voted for CORD were 300, and the number of female who voted for independent candidate were 50. Now, there is what we call marginal totals. The marginal totals are the totals we are going to get at the bottom here. So we are going to have totals here. And also, we are going to have totals here. We call them marginal totals. So we are going to have the total. So the total for this, we move across and we get 200 plus 150 plus 50. We get the total there. And the total down there, we move down. So we have 200 plus 250 we get the total there. So the total down here, we see we have 200 plus 250, we get 450. 150 plus 300, we get 450. And 50 plus 50, we get 100. Those are marginal totals that are coming at the bottom level, the total for every voting preference. Then we have the other totals. We get the totals for male who voted for Jubilee. We get the totals for male who voted for Jubilee, plus the total of those who voted, male who voted for CORD. Then we get independent, and we get the number is 400. We get the female, who are 250, who voted for Jubilee. Then we get those who voted for CORD, they are 300. Then we get those who voted for independent candidate, they are 50. Then the total there is 600. So we have the marginal totals, and the world total for these is 1,000 here. So this 450 plus 100 is 1,000. And when you get the total on this side, 400 plus 600, you get 1,000. Now, how do we use these values? How do we use these marginal totals? Now, these marginal totals are going to give us now the expected frequencies. The 200 is observed frequency. The 150 is observed frequency, and 50 is observed frequency. But now these marginal totals are going to help us come up with expected frequencies. Now we draw it against the contingency table so that we can now move in and calculate our expected frequencies. And this is how we move on. We take this total on this left side, 400, times this total at the bottom here, this total at the bottom there, then we multiply together. So this is 400 times 450 all over 1,000. 1,000, as I told you earlier, is this value that is forming a total for all of it. So that is the value that go to the denominator. So here we have 400, which is here, times 450 all over 1,000. You get 180. This is 180 is the expected frequency for this cell. Expected frequency for this cell. Then we move to the second cell. The second cell, we take that same value as a total here, multiply by the value down here. So it's 400 again times 450 all over the total there. The marginal total at the left and the marginal total at the bottom are over the, all over, which is the denominator, all over the total, the whole total for the two. Then we also get to the last cell, the independent cell, there, cell number 3. We have the total here is 400 times 100 at the bottom. So it's 400 times 100 all over 1,000, which is 40. We move again to cell number 4 and do the same thing. So the total at the end here, my left end here is 600 times the total down here is 450. So 600 times 450 all over 1,000 gives us 270 as expected frequency. Then we move again, 600 times 450, the total down here. This total down here, we bring them here. That one goes there, and this one comes here. So all of 1,000, this 1,000 comes from there. Then we have 270 as expected frequency. And finally, 600, which is the total, marginal total at the end, from plus times marginal total at the bottom, all over 1,000, we get 60 as the expected frequency. Now, after you have finished this, now realize that in this, we had 200. This is the observed frequency. And we have calculated in the same cell the expected frequency. So we move on now to come up with another table. Now, this is the table we are coming with to record in cell 1. Cell 1, this is our cell 1. Cell 1, this is our cell 1. Cell 1, the observed frequency is 200, and the expected frequency we calculate is 180. So we come up now with a table and we record the observed frequencies and expected frequencies. So in cell 1, the observed frequency is 200, while the expected frequency is 180. In cell 2, the expected, the observed frequency is 150, while the expected frequency we calculated is 180. Also, in cell 3, the observed frequency is 50, while the expected frequency we calculated is 40. And in cell 4, the observed frequency is 250, while the expected frequency we calculated was 270. And in cell number 5, the observed frequency was 300, and the expected frequency was 270. And finally, in cell number 6, the observed frequency was 50, and the one we calculated was 60. So now we are going to get the observed frequency minus the calculated frequency. So this will be 200 minus 180. This will be 150 minus 180. Then this one will be 50 minus 40. This one will be 250 minus 270. This one will be 300 minus 270. And this one will be 50 minus 60. So this 200 minus 180, it will be negative 20. So here you'll have negative 20 squared. So you have to square this one here. This one will be negative. This one will be not negative 20. It will be 20 squared. This one will be negative 30 squared. Sorry for that. This one will be 10 squared. This one will be 20, negative 20 squared. This one will be 30 squared, and this one will be negative 10 squared. So really the first one was 20, 200 minus 180 is 20 squared, not negative 20 squared. Then you will get here will be 400. Then here, this one will be 900. This one will be 100. This one will be 400. This one will be 900. And this one will be 100. So having finished filling your table, you'll get something like like this one here. So now I want us now to get the, we have to divide everything here by expected frequency. So this one will be 400. You are dividing by expected frequency, this one 80 here. So you are able to get 2.222. This one will be 900. All over expected frequency. Expected frequency there, it's 180. This one will be 5.00. Then you have here observed minus expected. This value here, 100. All over the expected in this case is 40. You get 2.5. Then here 270. Observed 250, not 70. 200 and 400. We calculated here, it's 400. All over the expected 270. You get 100.481. And this one is 900. All over the expected is 270. You get 3.33. Then here we have 100. All over 60, which is the expected. So you get 1.667. All these values, add them. 2.222 plus 5.00 plus 2.500 plus 1.481 plus 3.33 plus 1.667. You get 16.206. Now this is the chi-square calculated. This is the chi-square calculated. The chi-square calculated equals to 16.204. We have not finished. We have to move on now and get our critical values from the tables. And in order for us to get the critical value from the table, we have to calculate the degree of freedom. Now, the degree of freedom here, we have how many? We have how many columns? We have columns. We have 1, 2, 3. There are 3 columns. So 3 minus 1. And how many rows do we have? We have 1, 2. There are 2 rows. Then we have 2 minus 1. So 3 minus 1 is 2 times 2 minus 1 is 1, which is equal to 2. So our number of degree of freedom in this case is 2. The degree of freedom in this case, it's 2. Now we move on now to get this value, the value from the tables. Now these are our table. And when you see the table, it has a P up here. And this P represents the level of significance. P represents the level of significance. And on this side, we have degree of freedom, DF. We have 1, 2, 3. So the number of the degree of freedom that you've calculated comes on your left side. And we have 1, 2, 3. And on top, we have your P value, which is the level of significance. And in this case, our level of significance is 0.05. So we identify, we have already calculated here, and we have seen that the degree of freedom is 2. So we move here and look for where 2 is. So we have a violated 2 there with a red color. Then you move across, and then you get where your significance level of significance is, which is 5 there. Then where the 2 values meet, the level of significance and the degree of freedom, they are meeting at 5.991. They are meeting at 5.9191. So we have the degree of freedom, which we calculate those 2, and we are looking at this value at the level of significance of 0.05, and they are meeting at 5.991. So this is our critical value, or the table value. So we are going to compare what we calculated 16 point, what we calculated earlier as our chi-square 16.204, and this value we have just gotten 5.99. We compare them and we see whether we are going to reject our null hypothesis or we are going to accept our null hypothesis. Now, before we move on, I gave you the criteria, and you know the criteria we are going to use. I talked of if the chi-square calculated is greater than the table value, then we have to do a decision. Which decision were we to do? Which decision? You know, now, let me help you to get to the decision. Now, this is a normal distribution. And the other day, when we are looking at the distribution, we saw that we can put these 2 values that we have on this normal distribution. And this is how we use our normal distribution in knowing or rejecting the null hypothesis. Now, we have 2 values here, 5.99. The 5.99 is the value we have gotten from our table. That is the tabulated value. And we have another value here. And you know, we are tabulating from them from 0.0. So we have 0.0. And as you are moving on, you get 5.99. Then you get 16, which was the calculated value. We get 16, which was our calculated value. Then now what do? We see that if we got the value, if this value 16.0 16.2 was less, then it will fall in a region in our normal distribution. And this is what we will do. This is what our decision look like. If that value was, and it fell in this part of the normal distribution, then we will have to accept our null hypothesis. But since that value is greater than and is beyond our tabulated value, then our decision, that value falls there, and then our decision will be to reject the null hypothesis. You see that where that value is falling on our normal distribution? It's beyond our critical value, 5.99. And because it's beyond our critical value, then it's falling into the rejection zone on the normal distribution. If that value was less than our critical value, we will accept the null hypothesis. But because it's beyond our critical value and it's at 16.2, then we have to reject our null hypothesis. So in this case, the decision, our chi-square calculated value 16.204 is greater than our tabulated or our critical value at degree of freedom 2, and our level of significance 0.05, which is at 5.991. We reject the null hypothesis. We reject the null hypothesis. That is our decision. And when we reject the null hypothesis said that there is no association between the gender and the voting preference. So when we reject this one, then we'll accept the alternative hypothesis. Now, how do we calculate the chi-square, or how do we get the chi-square in our SPSS? First of all, you'll have to, in the previous classes, I had shown us how we enter our data in SPSS. So first of all, you have to prepare variables. And after preparing your variables in the variable view, now you'll go to the data view, and we have the coded here gender, and the male is represented by 1, and female is represented by 2. And the political parties, because we have 2 political parties, 3 political parties, we have Jubilee represented by 1, God is represented by 2, and Independent is by 3. So after entering all the samples in the SPSS, now it's time to calculate our chi-square. Where do we go to get our chi-square? Go to the analyze. Go to analyze. Then after you have clicked on analyze, it will bring you a drop-down menu, and this drop-down menu will give us descriptive. So you go to descriptive statistics. Go to descriptive statistics. Then when you click on descriptive statistics, it will bring us another menu. On this menu, go to crosstabs. On this menu, go to crosstabs. Now, after you have clicked on crosstabs, it will bring you another dialog box. And on this dialog box, go to chi-square and check that box on chi-square. Check that box on chi-square. And after you've checked that box on chi-square, then because you want to test the strength of the association, if there is, then you go to pi or grammar phi. Then go to continue. Continue. Then it will bring you after a short moment, it will bring you such kind of a table. It will have calculated for you the chi-square. So you don't go looking for these others, but you go the first one there, the Pearson chi-square. Then you look at the significance. You look at the significance. I'm not going to talk about significance right now, because I just wanted to show you how you go down to the chi-square and then have your value there. So in this chi-square, you have the degree of freedom as we calculated. Now this one also calculates for you the degree of freedom, DF, there is 2. And the significance decided is 0.0000. This one will discuss it later. We are not discussing now this level of significance. We'll discuss it later. But you can go and then look what it means when the level of significance is less than 0.05. What it means, and when the significance is greater than 0.05, what it means. What it means. That's some assignment I'm giving you. Look at the significance. When it's less than 0, when it's greater than 0.05, and when it's greater than 0.05. What does it mean? And how do you interpret the results at that point? Okay, I can give you, we can do another example very fast. Can do another example very fast. there was a poll conducted by a teacher in a school, and he was trying to find out the opinion of the students on the introduction of one uniform system of dressing in a second school in the state. The teacher sampled 1,000 students randomly from all the local government areas of the state. The results classified according to their ages, and they are given below. Now, the teacher wanted to see whether the age of the respondents and the choice of the uniform are associated. There's an association between the age and the choice of the uniform the students have to put on, because the uniform had to be introduced in a second school in a given state. So the researcher wanted to know whether there is a preference among the ages. So in this example, the ages were categorized as under 13, 13 years and above, 13 years to 16 years, and 16 years and above. And the opinion was, a respondent was to respond either yes, no, or undecided. Yes, no, or undecided. And there, as I said, there were 1,000 respondents in this study. So I have a contingent table here. And in this contingent table, those under 13, those who said yes were 106. Those who said no and were under 13 were 186. And those who are undecided, and under 13, there were 41. Between 13 and 16, those who said yes were 106. Those who said no, between 13 and 16, were 120. And those who were undecided in this category were 7. Then above 16, those who said yes were 152. Those who said no, they were 112 and 102. And those who undecided, they were 80. So the marginal totals for yes were 414. The marginal totals for no were 408. And the marginal totals for undecided were 178. The marginal totals for 13 were 333. And the marginal totals for 13 to 16 were 303. And above 16, the marginal total was 334. And the total for all the students were 1,000. Then we are going to come up with tables for observed frequencies and expected frequencies. So I will not come up with these, but differently. I just came up with the table that is showing the expected, because I'm going first of all to calculate the expected frequencies for every cell. So this is how we go on. So 414 times 414 times 303, that's 3 over 1,000. This is what we get. 408 times 333 over 1,000, 105.86. But then you do the calculation up to the end. Then you come up with a table like this one, observed frequencies. And in here we have 9 cells. Then we do have observed, expected. Then You have to do what we did previously. Then you have to get the totals down here. So the total is 52.907. Then you have to look, you have to get now the degree of freedom. The degree of freedom we're having 3 columns and 3 rows. Then this one will give you 2 times 2, and you'll get 4. Then you have your chi-square calculated is 52.907, and the one you get from the table is 9.488. So the chi-square calculated is greater than chi-square you get from the table. So the decision is you reject the null hypothesis. So you say, the null hypothesis says that there is no relationship between the age of student and the opinion over the introduction of the new uniform. So we reject that one and we accept the alternative hypothesis. Thank you very much for being with me in this class. It has been long, but I think you've gotten something. You can rewatch this video again and again so that you can be able to do the calculation, and also you can get your own example and try to calculate and see whether you grasp the use of chi-square. Thank you. Let us meet in the next class.